没有啊，他们明明走比我早。嗯，你看我刚才拍视频，又拍。还是 OK， 这么有垃圾桶在。Hello，要不要？
问你一个问题啊，一个 fine plane 里面啊，by Excel 嘛，我们最多只能造一个点，
最多只能告诉
一个点，
没有啊。
就从3个图里面只能造出一个点。
哦，
by Excel 的话，只能呢？
这样只能造就一点是那个点一定要存在，但是你可以再加其他点。对啊，你可以加其他点。
就这个3个如果符合求美秀，它就会有一个点。
对。
那同样东西我不能造出多2个点吗？
当然，但是都可以啊，只要符合那些。但是我想给他的 claim 是，
他说不可以。
我不是说不可以，我是说那3个点可以只是一个点。
对，所以就是讲我那个3个点就是其余2个点，其实我来造一样的一个点。
会有这种，我不是在说一定会，我只是在跟他说会有这种情况发生，就是可以有一个 fine plane 只有4个点，对不对？行。
fine plane 一定至少要有4个点，
但是可以有一个 fine plane 只有4个点。
是多于4个点的点，我是不可以去 assume 它。就是说，可能那个 plane 不够大。
对啊，我就是想，
就是
一个
assume 我的 fine plane 够大。
不可以，它有很多个可能性，
所以至少4个点是肯定要有啊，以大极小的好。
对。
但是第5个点、第6个点不一定。
这就是我 claim 的。
我很想要看出来，你知道吗？
什么叫看出来？
我想要画出来看。
画出来。
要
上课了，等会下课我跟你说。我刚不是跟你说了半天吗？
你昨天穿的这个后面就是
当时怎样证明他在看那个？
哎，对，没错。我会放 solution 看，我有空我会把答案。
有这个就有这个。
Okay, good morning to everyone. So have anyone studied the typesetted lecture note? Huh? No. Anyone look at it? There's a typeset version of the lecture note. Huh? Anyone know? Do you guys know the existence of it?
I think upload it very slowly.
Huh?
I must say that we upload it very.
Yeah, we upload very slowly. So
What if you have to tell me type lecture? Okay.
So somebody, your classmate, type lecture notes out, so that it's hopefully easier to refer. Have you guys written this yet, or do you know the existence of this file? Don't know. Okay, so this file is updated quite slowly, like what Eric said just now, because Eric is the one who typing it. So if you like, right, I encourage you to join him. Okay, to join him, type out the lecture note, because this is one way you do revision also. Okay, this is one way you do revision also, and by going through the argument again will make you more understand. Okay, okay. Like last time, right, I have Win Chuan also, master, helping me to type the general topology. Okay, in the end, got A. That's fine. So you can try and help type these notes. See whether you can find mistake or not. See you can fill the gaps or not. Okay, yeah. It's very beneficial for your study. Okay, especially if you're a person who like to type, who like to do typing. Yeah. If you like to type up your assignments, you are very good in latex. You can kind of help. If you're not good in latex, also you can come and do, right, because you could learn the technique also. Okay, you probably need latex for FYP, for your TCs, and so on. Okay, because latex will produce a better image of equations. Right. For example, 子谦, right? 子谦 like to type, right? You can help type. Maybe you can type faster, hopefully. Right. Yeah. Try to engage learning. That's why we have group project in this class here. Okay, so engage learning, not learning by oneself. Okay. This is about assignment. I know this is about lecture notes. Any question on assignments or not? Is it okay? Anything I want to ask? No? So we'll be due tomorrow, right? Yeah, hopefully you'll see your assignment tomorrow. Huh? General topology. Yeah. Yeah, we assume to be today. Oh, I think you're not in the class that day, but I make the announcement there. Yeah. Yeah, let me know if you cannot finish or not. Supposed to be last Friday. Huh? Supposed to be last Friday. Yeah, okay. So tutorial 3 is up. Tutorial 3 is all the questions are leading to why once you have a maximal independent subset of field, okay, you can make your field make your field a finite dimensional vector space. Okay. And in the assignments, I asked you to prove Noether normalization theorem. And then there's the other way to prove you have a finite dimensional vector space once you found a maximal independent set. Actually, Noether normalization theorems. Noether normalization theorem actually takes this problem here. It exactly tells you how to find it. Okay. So you'll see a different way to prove it. Most probably your assignment 2 will need result from tutorial 3. Okay, I'll try to release a solution for tutorial 3 soon. Okay, you don't need to use the proof, but you need to use the result. But if I provide the proof, maybe you will understand better why these things works. Okay, no? Even if I don't release the solution, actually those are taken from the textbook one. Some of the textbook. I think okay, maybe I'll give reference later if I manage to have it. Another thing is we have finished projective geometry, okay, on projective plane, projective tree space, and then we move to commutative algebra a little bit. Again, doing PID, UFD. Okay, actually we won't leave commutative algebra so fast. Maybe in between we still need to introduce some tools in commutative but we will leave it later when we have more motivation. And this part of the course, we will deal with Hilbert now set okay, this is our goal. And then for this part of reference, you can go to Mouse-Street Algebraic Geometry. I already put on the folder. Okay, so if you want to read advanced, you can read there first. Okay, so my goal was I try to prepare advanced material, and then I will show you what are the main reference I refer to, so that you can read beforehand. Okay, because I will read multiple references, but I will release a main one so that you can have at least something to follow. Yeah. Does that make sense? Yeah. All right. So we will continue from last lecture. So last lecture we stopped at last lecture. So last lecture we stopped at something called the zero set. Okay, zero set of function, or sometimes we write it as vanishing locus of f, okay, vf or zf here. So these are all the points. So these are all the points such that fx equals to 0. Where do we pick these points? So basically these points are picked from the affine n space. Okay, affine n space here. Okay, so these points are picked from R. Okay, so this is called the Z is the zeros locus, or sometimes we call it a vanishing locus. Okay, or F. And sometimes, right, we could consider multiple functions together. Okay, so we could put F1, F2, and so on. Okay, there's no restriction of amount you can put here, but then this set here will become a common zero, a point that you need to solve for these solutions such that they equals to 0. But obviously, could you imagine if I put everything here, every fi here, then what will set become? What do you think? What do you mean by 0? Set becomes 0. Just 0. Okay, so you claim it's this. Okay, let's say one of my function is a constant function. Right. Right. So there's no point that satisfies this equation to be 0 here. Okay, so it should be empty. Okay. Okay, so if you put too much restriction, actually you are dealing with empty set. I give analogy last time about. I give analogy in this one. What? If you put too many restrictions, you cannot find a girlfriend. Oh, seminar, I put in the seminar. I mean, there's a Chinese idiom here, 水之清而无鱼. Okay, you're too clean also cannot. No fish can live inside it. Okay. Okay, so well, you see, so how many variables exist here? So well, we can consider different n here. Okay, so we can consider different n. Okay, n equals to 2, 3, 4, or even 1, right? And so on. And we can consider different K here, different field here, R, C, Z mod 2, right? And so on. And we can consider different number of Fi here. Okay. So all these different variables here, we have a name associated to these set. And we call it set first. Okay. Yeah. These are all the classical stuff that people studied. Okay, up to this day. Okay, so there are a lot of names for them. Okay, we will go through some of them. Okay. So let's define subset Y, okay, of A and K is an affine, or sometimes we just refer it to algebraic set if there exists a subset T in A. So have I introduced the notation A? I think so. AN here. Okay, such that Y equals to Z. So if you are a zero set of some polynomials or set of polynomials, then we call you a affine algebraic set. Okay, so how to remember this terminology here? Algebraic, right? So whenever you think of algebraic word in this this course, you should think of some polynomials. Okay, so these are the points that solve the polynomials in the zero. Affine here, okay. So affine here meaning we picking these points from affine space. Okay, so affine algebraic set. All right, so let's go through some examples here. I'm not gonna draw them, but you see some picture. Okay, first, very easy. We start from one polynomial first. Then let's start from the coordinate of t equal to 1. Just one polynomial. And then we will call this an affine hypersurface. Okay, for example, the easy hypersurface you see before in your AH is a con and x squared plus y squared minus z squared equals 0. So you see, now usually we write the variety. Okay, don't want to say variety. Affine algebraic set as a v of some polynomial. Okay, instead of saying that this polynomial equals 0, all the polynomial that's satisfied. Okay, so this is a convenient way to tell this set. Okay, usually in the calculus, right, you write this set as, for example, all the x, y, z in, let's say in this case C3, such that this point satisfies the equation equals to 0. The polynomial equals 0. Okay? But we will just denote this as the v of something, v of this polynomial. Okay, so save your time. So whenever you want to think of this kind of polynomial equals 0 set, just write v of something. Okay? So, true. Yeah, true. Yeah. So sometimes, right? I mean, very often, the picture we produce here will be in R, okay, instead of in C. Because if it is in C3 here, C3 is one C is a two-dimensional real manifold, right? Okay, so C3 will be 6-dimensional. We cannot draw 4-dimensional and beyond. Okay. So if you have just one equation, we will call this affine hypersurface. Okay, hypersurface. And if n equals to 2, so let's say we what is n here? We just consider our affine space to be 2-dimensional, okay, as a vector space, 2-dimensional. Then we will call it a affine plane algebraic curve here. Okay, still one function. Okay, so how many affine plane curve here you can see? For example, the circles. These are in 2-dimension. The bottom one here also in 2-dimension. And if your field turns out to be CA, then this is the thing that you study in complex analysis. We call it a Riemann surface. And in F, let's say your F, we restrict it with a degree 2 at most. For example, the circle degree 2, you see the highest degree there. Parabola also, if you look at the x squared there, xy hyperbola times together, total degree is 2 also, right? Okay, then these curves are conics. So what are the conics? For example, ellipse or hyperbola. So ellipse include the circle and also parabola. So these are the things you study in calculus. Okay. And there are degenerate case here. Okay, so what about if we increase the degree of your function? So degree 3, so you can look at this picture here, all have degree 3 monomial terms here. Okay, so these are the curve we call cubic. Okay, cubic because power 3, right? Degree 3 cubic. Okay, cubic. So one of them is called cuspidal curves. Cuspidal curve. So if you look at the y square minus x cube, is the figure 2 here. Yeah, so this is called cuspidal curve. So where's the cups here? So actually the cups they're referring is this point here. Okay, which you have a singularity. Hopefully you can see later the singularity there. And then a nodal cubic. So nodal cubic is which diagram here? So it's actually the first diagram here. So there's a nodal cubic having a double point. So where's the double point? You can see that at the origin, right, it comes back twice. Then come back twice here. And then lastly is the one that we introduced last week, called the elliptic curve. So it's one of the examples of this elliptic curve. So these are the curves that has no singularity. And so double point cups, these are the singularity. Okay. Yes. So again. Yeah. Yeah, it should be. I think it's how it defines. I think one of our group do elliptic curve, right? Which group? Jingsen. How Tian. Yes. Okay. So maybe you can answer his question later. You'll find it. Okay. So you can see that you can define actually a family of elliptic curve here based on this parameter lambda here. Okay, so you can see that. What do you see here? If lambda equals 0, you will have a curve plus a point. Okay. When lambda goes -1, the point seems to grow into a loop. And then when lambda equals 1, it becomes just now what you call an order to be like that. And then lambda equals 2 is the circle split up again. Okay, so you can consider the family of this, which we call the moduli space. And we can consider them at once. Okay, how about higher degree? We can keep increasing, right, the degree of that. So we can draw something else. These are also the picture you draw in computer school and the roses. Actually, you can use the algebraic polynomial to write it down instead of using, what do we use last time? We use the what coordinate that? Polar coordinate, right? What time we use polar coordinate? Okay, so you can do the change of variable back to x, y, z again. A bit messy, but still. For example, first one is the trefoil. Okay, trefoil is the basic subject we learn in log theory. Trefoil, first non-trivial log. And then the other one, four roses. Yeah, 4-leaf roses. I mean, okay. There are more on the affine plane. When we increase the dimension of our space, then these hypersurfaces are called the surfaces section. So these are the surfaces. For example, you will call this the 2-dimensional thing in 3-dimensional surface. Okay, so we increase your space ambient dimension to 3. Then this hypersurface is just the surface you know every day. Okay. And hypersurface of order 2, right, are also called quadrics. Okay, so if you read about quadric surface, actually they are referring to the polynomial with degree 2. Okay, so these are very standard word you can see in literature, even until these days of research articles. Okay, for example, these are all the quadric surfaces. Okay. So I give some more picture to you. You can decide what are plane curve, what are surfaces here. Okay, based on the degree of the function polynomials, and also based on the affine space you consider with. Okay, where's your solution set living? Okay, which space, which dimension? Okay. Yeah, there are more. Okay. Next one. Let's say we just restrict to degree 1, and then you have just one function where you say that this is a hypersurface, right? But in fact, you can call it a hyperplane here. And when n equals to 2, it is actually the line. Does that make sense here? For instance, the line defined by this. So this is the line is also a hyperplane. Okay. So in general, the first sentence there doesn't depend on n. Okay. Whatever n you have, as long as you have one function, and then this function is degree 1, we call it hyper. Okay. And then when n equals to 2, this is just a line. Okay, so because a line has a degree 1, ax plus b1. Actually, it's a hyperplane in K2. But usually we just call it line. So let's change some variable here. Let's say we have more than one function to consider. Okay, so the cardinality of t is 2. And we go to higher dimensional space. Let's say 3. Okay, it's around where we live. So it generally describes a space curve. Okay, so this is a space curve. So this is also some example from calculus, right? So twisted cubic curve here. If you look at these two parametric equations, if you set y minus x squared equals 0, z minus x cubed equals 0. So you parameterize it using what? X equals to x, y equals to x squared, z equals to x cubed. So actually it is a zero set of two polynomials. Okay, where x is free. Okay, so you can see that t is free on the other side. Okay, next we'll do a non-example. Should I write these down? Maybe not. Okay, just quickly go through. Not all the curve in R2 is algebraic. Okay, so for example, maybe you can give some trigo function here. Y equals to sine x. Okay, y equals to sine x, how do you draw it? Function like this. Okay, going on. But how on earth you said that, hey, cannot write trigo as an algebra polynomial. How on earth you're going to prove this? Okay, so see what's the technique used here. So we'll suppose that it's algebraic first one. Okay, the usual math trick, right? You cannot do it, suppose you can do it first. 你拗不过他，你就先跟他说，等他说有问题，你跟他讲，对不对？就这样子。It's like that one. In real life, somebody you cannot fight with them. You fight also no use one. They don't want to listen to you. You just follow what she wants. And then you prove that somebody is wrong, that person is wrong, then she will be happier. So suppose that x is algebraic. Let's say x is equal to some zero set of some polynomial. Then what to do here? Okay, so there exists a polynomial, okay, in this set such that f is not 0. Is this true? Such that f is not 0? Yeah. What does it mean by f is not 0? What am I writing? 又讲 zero， 现在又用零，现在又不用等。F is not equal 0 means what? This is not a 0 polynomial. Okay. So you don't pick a 0 polynomial. Maybe I put the double tree here. Better. Not equivalent to a 0 polynomial here. Okay. Do you know what does it mean by not equal to 0 polynomial? Yes, it could be 0 at some point, non-zero at the other point. Okay, not 0. And so what do you get here? And so x will be equals to vt. Okay, I keep changing notation here. Maybe I will try to be consistent in one of the in one paragraph will be consistent in one whole argument here. If I use z, then use z. Don't change z and v randomly. Okay, so x could be equal to the 0 set of some subset here t, but this is equal to what? The intersection of all the 0 set, because you need to be a common 0 for. Okay. Well, this just says that this 0 here should be in the 0 of f, because 0 of f should have more points. But notice that what can you do here is there's a very clever way here is if you put a horizontal line here. If you look at y minus c here, what you can see here is this intersection is infinite. Yeah. Okay. For any line in between this minus 1 and 1. Okay. Okay. Now we'll choose C such that fx comma c is not a 0 polynomial. Okay, what does this mean here? Let me read a bit advanced. Well, I mean, so when you do intersection, right, with this y equal to c here, what does it mean when you intersect with this curve here? Meaning what? Okay, let me ask you a question. What happened to this x here? These x. Draw them. Let's say here is x0, x1, x2, x minus 1, x minus 2. This si. This xi satisfy what? Sin xi equals to c. Okay. Okay, so this is what this x comma c here means. Okay, so it says that choose c such that, let me write here maybe, sin x c is not 0 polynomial. Okay, but the solution to this is finite. Is this finite? Is this finite or not? Wait, what am I doing here? Sorry, I cannot say this is equal. So, well, let me put here that these xi satisfy this point here. Satisfy this point here. Okay. So, wait, maybe look a bit messy to you. Okay. So let me draw here again. Okay, let me draw the idea to you. So let's start from two-dimensional affine space, and then we have a curve y equal to sine x. Okay, so in this class, right, almost you want to see it as y minus sine x equals 0. We have 0 cells, some polynomial here. Now you are supposing, right? You are suppose there's a function. Okay, there's a function or there's a polynomial function. Okay, call it polynomial. Suppose there's a polynomial f that's that is okay. Let's say fxy that is equals to y minus sine x. Okay, equal. Yeah. Okay. Does it make sense? Suppose, I mean, you want to show it's algebraic, right? Suppose this is an algebra, this is a polynomial. Okay. Suppose this is a polynomial. Okay. Okay. Yes. Yeah. He has element. Sure. It doesn't matter. Doesn't matter. I mean, we want to show you that you cannot even find a t. We haven't finished our argument. Yeah. Okay. So suppose that we can write this as one polynomial here. I mean, we want to achieve. Okay. Oh, I think I get what your question asking about. Let me think. So how should I put this? Suppose. Okay. So I think we can just. Okay. I think you're right. We cannot say this. But what we can say is the zero set of y minus x sine x, right, should be the zero set of this guy. Okay. Okay. I think I get what you said. Okay. We can only say this. Okay. But if you look at the point sine x equals to c, okay, this has not that sine x equals to c has infinite solution. Yeah, no. But if you look at fxc equals to 0, how many solutions you have? This is a polynomial. And much as the degree of polynomial, but your polynomial can have infinite degree or not? Cannot. Okay, so no matter what c you put inside here, this polynomial, you can only have finite solution. So you cannot have an infinite solution inside this finite solution. That makes sense. Okay. No matter what t such that fxc equals 0, the 0 of fxy is finite. Yeah, because this is a polynomial. Our polynomial only have a finite root because your polynomial is of finite degree. Okay, no. Okay, so this is one of the skill to prove something is not algebraic. Okay, so the proposition here is you can generalize this statement here. So if you have an algebraic R5 plane curve here, and then you have a line that is not inside this plane curve, then the intersection between the line and the R5 plane curve here is empty or it is a finite intersection. Okay, or not? Okay, I cannot be infinite. Based on what we had just now. Okay, because the intersection should be less than or equal to the degree of some. Okay, does it make sense? Okay, so this is one of the technique you show something is not. I mean, R5 plane curve. I mean, yeah, showing something is not algebraic. And then in this case, we see how do we characterize these R5 plane curve. Okay, any questions so far? Questions so far? Okay. Okay, then we'll continue. So we'll go introduce R5 algebraic set to you. Now we will look at some property of these affine algebraic set here. So we will study the property of affine algebraic set, the zt, okay, or the vt. So this section here will lead to what is called the Zariski topology. We won't use much yet, but the property we introduce here will build up this topology. Okay, so we will build the property one by one here. So first lemma you will see is, at least you should think about it. So if I say, if we have two subset, okay, of affine space here. No, sorry, this is not the affine space. This is the polynomial space. Okay, if x is a subset of t, okay, then what do you think about zt and zs? What do you think? Who is larger? Which one containing which? S containing t means what? Eugene? S containing t means what? Right. So everything S had T also had. Okay. So potentially T has more function, more polynomial than S. So just now we said already, right? You have more polynomial, more restriction. Meaning what? Yours, more girlfriend. You sure? Less girlfriend, right? So less solution. Less solution. Okay, so you will have inclusion on the zero set the other way around. Okay, zt is in zs. Because why? Every solution that solves the polynomial in T must solve the solution in S. Right? Okay. But you need to remember these include, we call this inclusion reversing. This is a property that we'll keep seeing in this course here. Okay, inclusion reversing. Okay. Inclusion reversing. Right? So if you apply Z, it is an inclusion reversing. So it reverses the inclusion. Okay, so you are so good already. So this one left for exercise. Just now I say in Word already actually. Just one line proof only. Every solution that solves E solve X. Okay, next one. Next, every affine algebraic set X in ANK, okay, is actually the what? The zeros, okay? The zero set of an ideal, actually, okay? In these n what do we call this? Polynomial in n variables. Okay. Such that is. Okay, so if you take any subset of your polynomial ring of n variables here, then if you look at the zero set of x, it's actually equal to the zero set of the ideal generated by this x. Okay. Yeah. Actually, this is also not hard to think about, right? It's not hard to think about. So let me prove some proof idea here. I mean, up to this stage, you should know that this is a two-way inclusion, right? You should show two inclusion here. Okay, so let's talk about the idea. Why is this true? So if you satisfy x squared plus y squared equals to 0, right? For example, should you satisfy any function that multiply to this evaluate to 0? Right. If you have another function that equals to 0, that let's say gx. If you add these two 0 together, you still get 0. And basically, this is the definition of your ideal already. Okay or not? Does it make sense? Okay. Can you generalize this argument here? Can you generalize? Okay. Let's try. Let's try proving this. So two direction, right? So you need to show zx in z. There jet of the ideal generated by x, and then the other way around. Okay, two direction. So just now I prove a lemma, right? Okay, so supposingly you should use this lemma here. Okay, so now you're gonna show that two common zero is the same, but which inclusion you had if you can apply this lemma here. How do you apply lemma here in this case? So the question is, x is larger or the ideal generated by x is larger? Ideal is larger, right? So x is always contained in the ideal generated by x. What? Around where? What do you mean? Okay. You guys know what is ideal generated by a set or not? Don't know also. Okay. So how do I put this up? So basically these are the let me think. The linear, you can think of it as a linear combination of Ri, Fi. So let's say I equal to from 1 to something such that Fi is in S. Yeah. I think this should be enough to generate the ideal. Yeah. Where these Ri's is coming from your, in this case here, coming from your field. Wait, let me think. Sorry, not coming from your polynomial ring. So this is the ideal inside a polynomial ring of n variables. Okay. Does it make sense? Okay. So in this case here, which contain which? So we have the ideal of common zero of ideal is in the common zero of. Okay, so we have this direction here easily. So this direction here is this direction here. Okay, so we have z of ideal generated by x containing z of x from previous lemma. Okay, so the other direction, what do we want to show here? We want to show that x is in the z generated by x. Okay, so about this direction here, obviously you need to take any point from your the S. Okay, you want to show that it solves all the points inside solve all the polynomials inside the ideal generated by x. But what is the polynomials in ideal generated by x looks like? Like what I told you just now, right? Sum of sum Ri Fi such that these Fi are living in S. Okay. But then G of P is what? You just evaluate your Ri at P, Fi at P. But Fi come from S, right? So it's just RIP times a bunch of 0. If you like, I write it. which is 0. Okay, does it make sense or not? Hey, until this level, you should be able to see this kind of general segment. Imagine a simple case, and then if you imagine a simple case, do the general segment. Okay, so you should be able to do this in your mind now, actually. Okay, no? Does it make sense? Because in undergrad you like follow. But now after you can do everything, right? Try to think about why you do that. Okay, what it really means. Does it make sense or not? Okay, in the example there, I only take F1, F2. It's only 1, 2. Okay, F1 and F2. And then the other example is the Ri is the F there. Okay, sorry if the notation is too close, but you should see it. Okay. So this one is just a single terms here. Okay. And then there are two Fi there. Correspond to. Okay. Okay. Yeah. All right. What time is it? Okay. Before we take a break, let's mention another theorem here. So this theorem is pretty interesting. So it says that how do you get a affine algebraic set? So just now, if you look at one of the examples, right, the space curve, okay, actually is a zero set of two polynomials, right? S equals to x, y equals to x squared, z equals to x cubed. So in general, right, if you want to look for this affine algebraic set, it is actually the intersection of a finite number of hypersurfaces. Okay. So what does this mean? So just now we say what is hypersurface? A zero set that defined by one single polynomial. Okay? One single polynomial here. So in other words, this means that every affine algebraic set in obviously A and K here, algebraic set can actually define by just using finitely many polynomials. Okay. Obviously, we don't want to talk about the infinity case. I mean the empty set case. Okay, but the rest is just finitely many polynomials. Okay, how to prove this? How to prove this? You have to say something. Hilbert basis theorem. What does Hilbert basis theorem say? What does Hilbert basis theorem say?
If a ring is not theorem, then R joins the X is not theorem.
Now theorem means what?
Every idea is finitely.
Every idea is finitely generated. Okay, so just now we showed that every algebraic set is a zero set of some ideal. But if K is Noetherian, this ideal is just finitely generated. Finite generator means what? You have only finitely many generators. Okay. Then you can look at the zero set of these generators. Yeah, okay, so this is a follow from Hilbert basis. Sure. Okay. By the way, we always consider Noetherian ring here because the K we consider is always a field, which is a PID. Okay. Any question? Any question? No? Clear? Question? Okay, let's take a break until 1:02. Eric 啊，你可以发给我一下你们组分的那个分工啊，发了哈 ，OK。Yes. Yes.
Question.
Mhm.
How many more open sets than closed sets?
More open set than closed set. 真是
It doesn't
嗯
in like normal topology.
给我想想，我们还没有我们 define 了吗
Open set, closed set.
？OK， mine 我们 define closed set as the complement of open set。意思说每一个 open set 其实我都有一个 closed set。可能现在的问题就是说，会不会有不同的 open set define 一样的 closed set？应该是不会，因为我们用 complement 来 define， 应该是一样多吧？一样多，因为我们用 complement 来 define。
这样其实 like Zariski topology 跟 normal topology
我们没有介绍，但是有什么分别 ？normal 怎么没有分别啊？它就是一个东西的 satisfy topology 的 property， 就这样。你切了什么？像我跟你讲，分身。
I don't know if that's enough. Verify.
我不懂它的 context 什么啊，但是如果我们要讨论的话，我们可以讨论在同一个 space 上面放不同的 topology， 然后比谁的 open set 多。因为这个 Zariski topology 是 define 在 affine space 上面，但是这个 affine space 如果是 Euclidean space， 我们是知道它的 Euclidean topology 就是用我们的那个 metric 的 open ball 来做。然后以这个情况的话，这两个 topology 不同的 topology 在同一个 space 上面，我们就可以比较说，你的 open set 我有没有？
然后你会发现 Zariski topology 的不同的地方，就是我们不用 metric 来量它，我们是用它 satisfy 什么 point。
就是说我们 declare 谁是 open 就好，像是我们最后讲到嘛，我们只要讲谁是 open 就好，然后那些 open set 要符合那个三个条件。我找 Zariski topology 就是这样做，没有讲 metric 啊，没有跟你讲怎么重叠，告诉你属于 open 就好。
我在这里
portion 里面，把切出
哎呀，你可以想它是切啊，不是 portion 啊，但是肯定是把一些有用的东西组在一起。肯定是 ，yes。
是这样子，它切了就不会再重叠。
它会重叠，而且很大部分都重叠，所以这个重叠的怕就变成我们要study的话，其实如果不分，就是有时候我们要确保在重叠的部分上面它 behave well， 也是我们 define 的。在 intersection 的时候，就是说，假设我在这 open set define 了一些东西，在这个 open set define 了一些东西，然后我要把这两个东西 link 在一起的话，肯定它在 intersection 一定要是等于的嘛，不然的话就有 discontinuity 嘛，好像比如说我在这边是这样，在这边就是这样，这样你要选这个还是选这个呢？就是两边可以不一样，但是到这边的时候可能要一样，它才会接在一起。
我的后台就是还是有做 PR 的，然后有这个呢，这个类的，所以这个这个类我是
有人讨论
然后我
在比如 set 到这一种东西，
做 PR
应该是没有吧？像我告诉你的刚才，因为他们是 complement of each other， 你可以比较不同 topology 里面的。
我真的是
我都不懂对不对？这个东西，我不知道我不懂怎么做它。 我就去 DeepSeek 找，他就给我这个东西，他就这样做，然后我就跟他这样做，然后我就这样 prove 完。我这个方法是对的吗？还是错？
你要真的应该是这个什么是对的哎，这个是对啊，
这个是我设的嘛，我设他的嘛，我设他这个，然后
OK，
就是就变成，因为他就其实有点，我看他，因为他是给我这个，我的理解是，因为他的也是等于这个东西，所以我是他方向如果是一样的话，它是照不反，因为它大于零，它是 increasing 嘛。
没有，然后你加 apply 这个进来，
那你 apply 哪一个？
就是这个原理啊，这个你自己拿 t 大于等于零，然后它的 increasing 代表什么东西？
哦，这个啊，这你可以真有一个，
因为我想法是因为它 increasing 代表我带这个的时候，它还是大于等于，它就不会变了，因为它是 always increasing 的嘛，就还是大于零的嘛。你看，如果这个大于等于零的情况下 ，FT 是大于等于零。如果 FT 大于等于零的情况下，这个肯定是大于零，因为它不是那个它就不会变嘛，对不对？就是哪怕是零，它也这样可以有等于方向嘛。对啊，它这套就一样是小于等于咯，它就没有变。然后过后这个东西就是在 Kevin 说就用这个咯，这个就造就哦。然后过后我就想说，因为题目要求是 show 这个东西嘛，所以我就展开这个咯。然后就想说，因为这个去交换，因为这个大过这个嘛，然后这个也大过这个，这个我是这个大过这个的话，就代表这个大过这个。
对啊，
所以我就想我 need to show that 这个小过这个，所以我就把它这个移过来，然后就大于等于零，就做到后面我不想说，因为它大于零，所以它是对哦。
我也是这个。
对啊，I mean 你看这个你不用展开啦，因为你分开就好了嘛。你分开过后，这边跟这边的差别是什么？它 denominator 多了一些东西嘛。
这样讲分，
就这个分母是加起来的嘛？哎，sorry，分子啊。那你不是可以分成两个 fraction 吗？
哦。
然后你分成两个 fraction 过后，这两边相差的东西在哪里？他们分母吧 denominator，它分母多了一个这个 dy 的。
至少会是零或者。
对对对，
没有你就没有啊，就2加3 over 7两个，2 over 7加3。
就像你这个分两个，然后你这个下面少掉一个的话，这个一定要大于哪？
对啊，就是因为你少掉这个东西是 positive 的。
然后我这个下面变成就是它分等于一个是1加 dx Seng，然后另外一个是1加 dy 这个。
啊，对，因为你不见的那个东西是 positive 的，所以你肯定是变大的，就不用做这样多东西，不用做这样多 algebra。
算了。
哎，我回你，昨天那个应该是写漏一个 space， 所以就很奇怪，一直讲来讲去很奇怪。你看一下我回你啊，
你是不是把这个放在 union？它是要define 的，就那个 union 和 define 的后面。
为什么？
因为我这个地方是在用，就是因为你看我是在 intersect hyperplane， 但是它反而是 union of polynomial。
你是想完没有 proof 那一个？
对啊，所以我觉得你把这个放在那一个后面比较。
对，所以就是讲，
你试下把那个 proof 写出来。
就你讲的就是你 define pseudo metric on 你的 SN， 然后你 impose a metric 不是 on Rn 加1 but on Rpn， 是吧？
对。
他想要你 show 的就是让你 define 一个 metric 在 Rp 的意思和 Rp。
对，但是来
对
，AB 让我有一点点。
你的 topology 里的那个 remark 要做吗？
什么叫 remark？
这 topology 里面有个问题，不是写了个 remark 吗？他不是给你加了个问题。
什么啊？不用做也可以，没有分的那个，你要做就做。
做了有加分吗？
做了没有加分？
打死
我干嘛？现在学生想打死老师，我要去报警。啊？
就下面有那干吗？对吗？那个 B 是 win， 你没有写到吗？就因为你们也是写 ideal，M 是 ideal 是 B 嘛，然后里面的 B 是。可是既然你讲 ideal， 应该是 win， 我就。如果你有，还是你有 ID 过，我那时是蛮早下载。可以。
Oh, sure. I think
也不是形而是名，
也是名字，是名，那个是，我加个，
因为如果是 algebra 的话，B 可以是有，如果
呀
也是个名字，只是一样。
，OK OK， let's continue.
我写了什么？
Okay, next, we will define the sum of ideal. We define the sum of ideal first. Have we done this kind of definition before in AA1? Sum of an ideal. Not in class in the assignment. Okay, I also think the same too. Okay, so how do we define the sum of an ideal here? What do you think? How do we take sum here? What's the elements here looks like? What do you think? Sum what? Sum what? Sum all the generator. No need. We can be more general. Just sum of all the elements inside AI. But note that we don't want to take infinite sum here. I mean infinite sum of non-zero terms. So we would say that AI is not equal to 0 for only finitely many I. So meaning the finite sum here. Okay? Yes. Why finite? Why finite? If we take infinite, what happens? What happens if you take infinite? Well, I mean, for ring, right? For definition of ring ideal, I just tell you that if x and y in the ring, then x plus y is in the ring. By induction, this only works for finitely many. What's the infinite sum be? Not sure. You can approach, but not sure. So you see, when you ask about infinity, right now you're asking about like whether this element is inside the set or not. Then this is what question? What question is this? This is an analysis question. Right? This is an analysis question. Do you have this point inside there? Could be topology, but yeah. So yeah. Okay. So I mean, in ring itself, in ideal itself, we already not consider this case. Yeah. Although we will consider ring like a Lorentz polynomial or something like that. That started with infinite terms already. That case. Yeah, but in general, we just talk about x plus y. X plus y. What do you mean by general? General for what? In what sense general? For finite. So this is a finite sum. Because we don't want it to be like 1 plus 1 plus 1 plus 1 plus 1 plus 1 plus 1. Do you get? Yeah. Non-zero term for finite element. For example, 1 plus. So your question is actually the same as the here question, just that you put it in different way. So think about what is 1 plus 1 plus 1 plus infinity. What's that? Your question is the same as VDI, you know? I know. I mean, your question is the same question as VDI. Yeah, so now it's very important a moment here, try to understand what people say. Maybe people's already like ask you a question. Okay. Okay. So one thing is you need to check out this is an ideal. Okay, you need to check. So you need to do a sanity check here. This is an ideal. Another thing you can do is try check that this ideal, right, actually contain the union of II. Okay. Union of all the ideal is also an ideal. But this sum of ideal contains this union of ideal. And try and check this. A very nice exercise. This is a ring exercise actually. Okay, try and do it. Okay, next we're gonna prove something, some property that make it topology. Okay, the theorem here. So let ij and some index set of ideal be the ideal in A. So these are all the ideals in AN. So AN here is the polynomial ring of n variable. Okay, then there are following properties here. Okay, so first property is if you look at the zero set of a zero polynomial, okay, so zero polynomial means what? Whatever point you put it in, you just get zero. Okay, so meaning your zero set is just everything, every point. Okay, and then how about the zero set of all the polynomial? Just now we discussed already, right? If you just look at a constant polynomial, then you already have no solution, okay, to the zero equation, homogeneous equation. And so this is empty. Second, if you look at the zero set of intersection, okay, zero set of the intersection of two ideals here, then this is equal to the common zero of I union common zero of J. Does this make sense or not? I mean, unless, I mean, at least one direction. At least one direction. If you have a point that can solve every function in I to be zero and every function in J to be zero, okay, it should solve. It should solve I, right? Function in I to be zero and then function in J to be zero. But intersection means what? It's a function that live in both of these. Okay. So, well, I mean, from right to left should be easier. From right to left. Okay. How about left to right? Yeah. How about left to right? Well, I mean, you should just take any point from the left, right? Then you want to show that it also solves the function in I and in J. For any function in I and J. Okay. How about we just prove this first? Okay, let's prove this. So prove the second one. So first one discussed before. So let's prove the second one. So which direction is easier? So left to right. Okay, right to left. That's easy. Okay, now we're going to show the other direction. Z of I percent J in Z of I unit. Okay, so now let's suppose a point coming from the left. Okay. To show that it's in one of the common set, right? Just what do you do? What do you show? Either in one of the set. So we also suppose that P actually is not in one of the set. Then we need to show that it's in the other set. If it's not in one set, it should be on the other set. If you want to show that all segment is true, right? Okay, if one of them is false, the other must be true, so that these two is together is true. And suppose one of them is false, okay, it's not in one of them. Then we want to show that actually P is in Zj. Okay, so P is not in Zi means what? You are not a zero for all the function in I. Okay, so meaning what? Assumption there exists a function in I, so let's call it G, such that GP is not 0. Yeah, no? Okay, but so here's the trick. Here's the trick here. But moreover, if you look at all the F in J, what happens here? Actually, F of G is in the intersection. Why? Intersection of ideal is an ideal. So multiply by anything will also live inside the ideal. Sorry. Live in the ideal, why? Why is it living in the ideal? Because F in J, right? So GF is in J. But G is in I. FG is also in I. Okay. Does that make sense? Price can follow. Okay. Okay. So where do we pick this P from? P are picked from the common zero of I intersect J. So meaning what? F G on P should be 0. Meaning what? FP times GP should be 0. Okay, FP times GP should be 0. But GP is not 0. Therefore, FP have to be 0, which implies that P is in the common 0, the 0 of J. But not that here we use that actually our field is an integral domain. It's a field integral domain. It's a field integral domain. Yes, right. Okay. So we use the integral domain property here, actually. Okay, so if you change your K to different thing, not sure what happens. Okay, but our field is an integral domain. Okay, no? Any question? Yes. Why is the first direction easy? Think about it, no? Why the first direction easy? So what is the first direction? Can you tell me what's the first direction? Yeah. Yeah. Okay. So what do? You take a point from the left hand side, right? So either P is in Zi or P is in Zj. And then continue. If you cannot continue, right, work backward. Okay, don't continue, work backward. Okay, if you cannot continue, work backward. So work backward, what do you mean, sir? So your angle is P is in Z in I intersect J, right? Okay, this means what? This means that P FP equals to 0 for all F in I intersect J. Meaning what? Meaning that we join them together now. Is it enough to join them? Why is it enough to join? Anyone still stuck? And this is a very simple thing. You must unstuck. Otherwise, you cannot do harder stuff. You do all the harder stuff, is all fact one. If you cannot do the simple stuff.
I think if you see
Thank you.
that I intersect J is a subset of I and J, right?
Mm-hmm.
So Zi and J should be a subset of I.
So you use the lemma we proved just now, right?
Yeah.
Okay, so the lemma just now is really important. Although it's a lemma, lemma is very important. So yeah, so to be precise, let most of these things. But we know that I intersect J is in I and J, right? Okay, so just now says that Z of this what implies that Zi, Zj will be in Z of I intersect J. Okay. So you are either in one of them, then you are in the Z of intersection. Okay, if you still don't understand this statement here, you should go back to the lemma, try and write it down. Okay, because sometimes I need to correct you something. When do you say I know? When you know, you say you know, huh? But how do you make sure you know it? This is a very important question, you know. 怎样知道自己知道还是不知道？怎样知道自己明白还是不明白 ？Okay, one thing the student could take is 让老师决定我明白。我叫让老师决定，老师给你高分你就明白了，我给你低分你就不明白了。被人家决定，你的命运是被人决定。You should find a way to test yourself. OK， 可能我可以看得出很多你不明白的东西，But I'm also human only， 我只能够看到一部分吧，我也不是唯一标准，明白吗 ？OK， So you need to write down everything that you think that you know or you don't know. Actually, you need to write down. Okay, you need to write down everything you know and don't. Okay, and then try and compare. Okay, different solutions. For example, one way to check is like give solution right to assignment. Okay, you haven't met it because you haven't done the first assignment. Typically, sometimes always my solution could be different from yours. Okay, you can find all sorts of solutions. But try and understand why I can say like that. Why people do differently. Does it make sense or not? Okay. So actually you need to ask around one. You cannot just say, oh, this teacher tell correct. Not even the pro, the professional. For example, who created relativity? Einstein, no? If you go ask about relativity question, maybe he can answer all, You get what I say? So there must be something, how to say, something that people miss. And so this is the thing you need to feel it. You cannot say, oh, 老师讲我不用写，我就不用写了。就讲不用看就不用看。Okay, it really depends. It depends on what you want to do. If you're gonna do research, you're gonna find truth. You cannot follow that way. Because the thing that you miss is the thing you need in your research. This is based on my experience. Whatever I get stuck or confused, actually is the thing that I don't know. Once I know it, then I will accept it. You understand? Okay. And various people are stuck at various places, so you need to unstuck yourself. Does that make sense? Okay, so that's why I say university is like a self-study place. It's not like a high school anymore. Teachers say one, you do one, say two, you do two, say three, you do three. It's not like that. Because different people have different things. Okay. For example. Okay, let's continue. This thing is very important because if I don't say this thing well, you guys will just kick stuff forever. Okay, so you need to try and unstuck yourself. Okay. Lastly, I will see that. Have we done? Have we done yet? We done, right? Okay, we done for this part. Lastly, the set of the sum of AI actually is the intersection of the zero of all ideal. Okay. Let me quickly prove this. So the intersection of all the ideal, right? Okay, just now Eric said that I didn't prove this for you, right? So maybe you will left as a lemma for you to prove. Okay. So you can turn your intersection into a union inside. Okay. Then what's then? Then you can see that actually this is a subset of set of sum of I. Okay. Is this true? The other way around? Let me see. Have we? What's this direction? Why this direction is true? So well, I mean, okay. So let's do the easier one. Let's do the easier one. Let's do the easier one first. So just now we have an exercise, right? So since the union of all the AI contained in the sum, okay, then we have a inclusion, right? Inclusion reversing property that Z of the sum is containing in the Z of the union. Okay, in this direction here. Okay, so this direction only works for this part here. Okay, for this part, this is true. Okay, how about the other direction? How to get the other direction? Supposingly, I think I want to use this. Yeah. Say again. I think you can do it that way. Yeah, so, well, then should we talk about this? Okay, I think this one, leave it here first. Okay, leave it here first. So, well, so the claim here is the sum of this ideal is actually generated by this union of this ideal. See, does this help or not? If we have this,
if we have this, then we can put a Z on each side by the previous.
okay, let me see. So, which side we can put here? Let's see. So let's say before we proving this claim, how do we prove? How do we put the inclusion again? Oh, we would know that. Wait. First, wait. Let me arrange what we had now. This name, then this will imply that set of sum of ideal. Okay, let's not put this again. Is equals to the set of the ideal generated. Right, and then
this is equals to the union.
this is equal to what? The union of union. Oh yeah, okay. Set of the union of these. Good. And then we know that the union of this is the intersection set of IN. Then we straight away go equality, right? Yeah. So I was thinking using two-sided. Seems like I only got one-sided now. Okay, never mind. Okay, so if we get this claim, then basically we are done actually. Real or not? Okay. So is this claim easy to see or not? Left to right, right to left. So I guess right to left will be easy, right? So if you take the union of these things here, these are just what? Either you live in one the I, right? Then this is obviously a term inside this sum here. Okay, wait. So okay, well, okay. So let's do it. Let's do it. Proof of thing. So two direction you need to show. I think it's a if and only if, right? Seems like it's a if and only if statement here. Okay, so if you take a x inside sum of I here, what is this? This is if and only if. Okay, I think it's a if and only if. We say that x can be written as Ri times, let's say, AI, sum of this. Okay. But obviously, this thing is live inside the ideal generated by union of II, right? Okay, so maybe it's not clear what is in II here. So for some II in AI. Okay. And then everything in the ideal generated by II also looks like that, right? Then you can go backward. Makes sense. I mean, if you don't make sense, you can ask question. Yeah. I can. First of all, you know what I'm talking about. If cannot, I can repeat. Understand what I say? Understand? Okay. Once is you get my statement and then try and verify it. So either my statement is true or false. Okay, so you need to decide either my statement is true or false. If you think that it's false, and then you must have some argument, right? Then you can try and ask. Okay. Question? No? Feel free, it's okay. Okay. So once we have these, we have the equality that we like. So what do you see here actually? If you take union of common set, okay, is a common zero, then it is a common zero of an ideal again. Okay. And then if you take intersection, okay, intersection of common zero, it is another zero of an ideal again. Okay, so you can see that this affine algebraic set, right, is what? Is stable. Can we say stable here? Let's say stable here. I mean, behave well. Okay, behave well under finite union, under arbitrary intersections. So it behave well. So meaning it return to affine algebraic set again after you take union, after you take intersection. So what can we do here? Then we can define the Zariski topology. So Zariski here refer to a mathematician called Oscar Zariski. The hard book written by Harshon. Zariski is his supervisor. Yeah, he's a supervisor of Harshon. So we define the Zariski topology on ANK by taking. So topology usually we talk about open set, right? Okay, in this case here we will define what is open set in ANK here. So this open set here we were taken to be the complement. Okay, we don't straight away take affine algebraic set, but we take the complement of the affine algebraic set here. Why do we do that? Why don't just take affine algebraic set? So in the topology, right, the definition for open topology, right, you will ask for finite intersection of an open set is open, and arbitrary union of open set is open. But this is the other way around. But this the other way around exactly correspond to taking complement. Correct or not? A intercept B complement is what? This is a set theory problem. A intercept B complement is what? A complement union B complement. So complement help you to turn the intersection and union. Okay, so this also how we define closed set in topology. We define it as a complement of an open set. Yeah. Okay, so in other words, if you don't want to take Zariski topology as an open topology, right, you can just take it as a closed topology. You just use affine algebraic set to define a closed topology. So closed topology will be like the dual. We say dual of this open topology. Okay, so what it means by dual? So meaning you take this kind of property as your closed topology property. Instead of talking about arbitrary union, you talk about arbitrary intersection. Finite intersection, you become finite union. So topology is equivalent. You can use open to define your topology. Open set. You also can use closed set. Okay? Maybe this could be an exercise inside general topology. So these two topology define the same. Okay, you just mention either one of them. Okay, the other one should be the complement. Does that make sense? Okay, but so if any one of you learn more topology stuff, on ANK, right? If your K is like a real number, complex number, you can put a Euclidean topology there. Okay, there you have different open set. Those are defined, those are induced by the metric, the open ball. Okay, distance less than some number. Okay. Then we can compare, what? Compare open set on both sides. We can compare open set on both sides. Okay. Does open in Zariski topology means open in Euclidean topology or not? Or does open in Euclidean topology open in Zariski topology or not? Okay. Okay. It turns out that okay, we won't test this, but I want to give you some concept here. It turns out that the open set in Zariski topology is fewer than the open set in Euclidean topology. Okay. So meaning what? Every open set in Zariski topology, right, should be open in Euclidean topology. Yeah. Yeah. Why? Why? To give you some flavor, for example, let's give you some flavor here. Let's give you some flavor here. So for example, y equals to x squared, right? So this is a y equal to x squared curve. Okay, so in this course, right, we will be fancy a bit. We say v of y minus x squared. Okay, v of y minus x squared. What's the complement of this algebraic set? Everything outside y equals y minus x squared. Can you see this open set is pretty big? I mean, you can simply just draw a small ball around inside here. Right? Okay. So this complement usually is a union of a lot of open ball. Usually. So how to see in general? You need to prove. Yeah, you need to prove. Okay. Yeah, in general, I mean, we need to prove. If you are interested, I can put it as a tutorial question. Can, or we put it in the general topology class?
Can you define everything topology class?
Sure. Yeah.
Put it on general topology.
Assignment. Which assignment? General topology. Okay. Yeah. I think it makes sense for him to do. His stuff is on algebraic geometry. We'll see. We'll see how. If you guys really interested, then I can think of a way to make your wish come true. Okay. All right. So let's talk about what are the Zariski topology on A1 actually. So before that, actually you should see that all finite subset of AN are closed. How do you define finite subset here? You want a function that diminish on these points. Okay, so you just take the factors, right? Just take the factors, okay, that diminish on this point. And then this define a affine algebraic set. So affine algebraic set are closed. So we define closed to be a complement of open. Okay, so you complement of an affine algebraic set is an affine algebraic set. Okay, so a bit twisty here, but if you want to get a conclusion is closed here, just refer to the affine algebraic set. Okay. Open is a complement of it. Okay. Second, actually we can talk about what is the Zariski topology on the affine line. So on A1. Okay, what's the affine? What's the Zariski topology? Meaning here, what are the closed set? What are the closed set here? Actually, we can classify all the closed set. What do you think? Can you guess? What are the closed set here? So closed set means affine algebraic set, right? Z of something. But Z of something is equals to the Z of the ideal generated by those polynomials. So you need to talk about ideal generated ideals inside where? Here. In this case here, what's the ideal you need to talk about? Where these ideal live in? What's the function you consider for A1K? What's the polynomial you consider here? How do you get 1 point at least? What's the function space you consider? Last time we said that dually you need to consider what? A, the polynomial ring generated by one variable. You know? But ideal in Kx means what? K is a field. Kx field adjoin one variable is what? No idea. Noetherian, more than Noetherian. It is actually a principal ideal. So every ideal here should be principal. How to prove? How to prove? Yeah, use the division algorithm. Use division algorithm. Right? You divide, and then your degree must be less than it. And then you need to show that the thing left over should be 0. There's no remainder. Okay, so meaning what? So since every ideal is principal, every algebraic set should be a set of zeros of only a single polynomial. Because you can reduce all the ideal to principal. Okay, so it's generated by one polynomial. Okay, but furthermore, if K is algebraically closed, okay, if it is algebraically closed, then you really can split out all the roots. Okay, you can actually find all the roots. So algebraically closed almost equivalent to FTA, fundamental theorem of algebra, because C is algebraically closed. Okay, so you can split your fx into product of factors x minus a1 up to x minus a, such that these where these C AIs are in the field. Okay. Alright, so meaning what? Then your ZF is just a bunch of points. It's just a finite subset of your A1. So what are all the possible algebraic set here? So either finite subset, okay, either empty set, either the whole line. That's all. Okay, so don't imagine there's some interval. You cannot build interval using R5 set. Okay, maybe you can take complement. Okay, so, okay, say something to you. Okay, so if you have a line, right? Okay, so here what we identify for you was your R5 subset. I mean, yeah, your algebraic set, right? Should be some finite set, just a point. Or, so let me put here algebraic set. Yeah, A1 is either empty, okay, or finite subset, or the whole line. Okay, so you cannot imagine. I mean, you cannot imagine you are building some open interval like this using R5 algebraic set. I mean, using the zero of some polynomial, but you can build it out. You know, you still can build the open interval out using using the z of something. How to build one? Let me give you some clue. Let's say, for example, this is a very simple thinking here. let's say I know how to build this point here using f of some v of some f, okay? And then I want to build a open interval, say from this point onwards until negative infinity and infinity. Can I build this interval now? So let's say this point is x, such that x is 0. Can I build this interval from s to negative infinity and then union s to infinity? Can I build this? How to build? Can I build it? You know, you mean you want to write it as a v of something? No? Huh? Function? What do you mean function? Huh? Complement? Yeah. So you just take it as to be a1 complement vf. Okay. So what you see here is a open set can be produced by a complement of a closed set. Let's start with your equation. Complement of a closed is open. Okay, later we'll call these quasi alpha. Okay. If you have learned topology enough, this topology is also called the cofinite topology. Okay, because these are the closed set, right? If you take the complement, it is the open set are the complement of finite subset. Okay, so this is called cofinite topology also. I think we will have either assignment or tutorial in general topology on cofinite topology in general for general one. This is an example of cofinite topology. Okay, so Zariski topology in A1 is a cofinite. Okay. Any question before we finish? Any question? Okay. Let's see you tomorrow.